2p1 or 2p pi 1. And what is pi? It's a pi bonding orbital. So what should be the symmetry of this? If this is u and that's the only orbital I'm dealing with, what should be this fellow here? Therefore, if I ever ask you what's the ground state of a B2 plus system, B2 plus system will have as its ground state a doublet pi u state. So you can see that in some ways similar, in some ways very dissimilar. The way you build up states for atoms and the way you build up states for molecules sort of have a resemblance. There are differences, however, but then those differences stem from the fact that in one case you are looking at the orbital angular momentum and coupling those. In the case of molecules, you are looking at the projections on the nuclear axis and then coupling. The different effect becomes because of these two. But then, at the end of the day, given an electronic configuration, you must be in a position to be able to figure out what the term state of that molecule is going to be. The rest is straightforward. In the sense, if I give you this, what do you think would be the ground state for this? There are 6 states. Which do you think would be the ground state? First rule of Coulomb, what's that going to be? Highest spin. When it is highest spin, who wins? These 3. This guy is out. The first round, these guys are out. This guy is in. Now what do you do for the second round? Highest L value for atoms, highest lambda values over here, and therefore what would be the ground state in that situation? It will be a triplet delta. So if I gave you the situation of boron, B2 with a 2p pi, 3p pi excitation, and asked you what the ground state is, the ground state would have to be a triplet delta state. Because once you have the states, the way you determine the ground state is actually identical to what you did in the case of molecules. What I will do is, it's not too difficult, but the first time you see it, it could be a little unnerving. So what I will do is I'm going to send you a bunch of examples, work on them, and I will redo this whole thing all over again for you with those examples, so that you become more familiar with the way you can handle these states. But at the end of this course, you must be in a position not only to talk about the term states of atoms, you must be in a position to talk about the term states of molecules. So I've done a little tutorial at some point, essentially to take care of the term state situation. And we will look at the term states for a few other species, few other molecules, and we'll see how this can be rationalized. What I would like you to do at this point is you make your own molecules. You can start with lithium 2, B2, Be2, C2, and so on, and see what happens, and then see how you can actually come up with the term states for all these species. And we will do that in class at that point in time when we have the tutorials that I will essentially center around term states and related issues. Because this is not too difficult, but the first time you see it, it's not very convincing, and you have to really work a few examples before you actually start believing in the way the whole thing operates. Okay. So this is as much as I really wanted you to know as far as atomic and electronic spectroscopy of atoms and molecules are concerned. So we will stop here as far as this topic is concerned. Maybe we'll have a 10-minute break or something. We'll reassemble, and then we will start looking at the basics of NMR spectroscopy. And when we get back next time, it will become more quantitative. Today I'm going to deal with NMR spectroscopy rather qualitatively, just to get you a feel for it. And then we start with the quantitative aspects in the next class. Yeah. 5 o'clock, we'll be back by 5 days.